Okay, so hi everyone. I'm Alex, and I'm really, you could say, a hardcore Haskell user. So here on this slide, you see all the logos of the companies or projects I work on, and essentially most of the code is basically Haskell or something related like PureScript or Elm. So I really like Haskell, and I'm really lucky that I can actually work in Haskell in my professional time. All right, so let's start out with Haskell. I don't know how many of you are familiar with Haskell. Maybe you can quickly show your hands. And how many of you actually wrote some code more than Hello World in Haskell? Cool, so quite a bit people that touched Haskell. All right, I have to click here. All right, so Haskell is basically a functional programming language, right? It has static types. And with a good type inference engine, it has immutable data structures, green threads, and pattern matching. And well, often or mostly it has good performance. And so I just took this example from the Haskell homepage that you can see when you go to haskell.org, just to show you what Haskell looks like if you're not familiar with it. So here we define a function called primes, right? And what it does is, in the function, we define another local function called filter prime, which we give an infinite list that starts at 2, right? So you might ask, infinite lists, how is that possible? This program is never going to terminate. Well, as I said earlier, Haskell is a lazy language, so expressions are only evaluated when you actually need them, right? So in this case, you can think of this as a stream of numbers starting at 2. And then the filter prime function, what it does is it pattern matches on the list, right? So you write an expression that says, well, here is a list, and the list has to have a head and a tail, right? So the first element and all the other elements. And after we pattern matched on the list, we take the first element from the list, append it to the result, and then we call filter prime again. And as an argument, you might know this list comprehension from Python, right? We pass all the numbers from the rest of the list that are not divisible by the number we just added to the list, okay? And remember that this is a stream of numbers, not actually a list that is materialized as a list, so we can potentially get an infinitive number of prime numbers. And now it's our job in our application, for example, to only take the first 5 or only the first 10 and print them on the screen, to not get an infinite loop, right? So maybe you will wonder, well, is that really useful? Can you actually write production code with these techniques, right? I'd say yes, it's really useful, right? You can really use Haskell as a general purpose programming language. You can do front-end web development, you can do back-end web development, you can do concurrent and parallel programming, cluster computation, and there are a lot of banks that use it for financial modeling, and the list goes on. So Haskell's not a toy language or a language that was invented. It was invented in the academics, but it's also very practical to use in day-to-day work, and there are many examples, and we'll kind of look at these examples that I discovered in my journey. Right. So to start, we will quickly talk about learning Haskell, because I think this is a topic that gets talked about a lot. It's basically, I found this this graphic here that kind of has this comic-like graph what learning Haskell looks like to some people, and what my story basically is, I did a lot of PHP and JavaScript development, so I had nothing to do with functional programming. And I did an internship at this Checkpad company that you saw in the first slide, and that we'll also talk about the product in a bit. And I wrote a JavaScript front-end component. And then they said, well, nice component, how about you integrate it in our backend? Our backend is, by the way, written in Haskell. And I'm like, okay, sounds scary. Right. And so I was pretty lucky to have an awesome boss. And he said, come on, we'll go and we'll take 2 days and we'll do a Haskell bootcamp. So I'll sit next to you, we'll do pair programming, And when you come out of those 2 days, you can you can contribute to our Haskell code base, no problem. I'm like, okay, let's give it a shot. So we sat there in this room and we wrote a parser combinator library, and we wrote a small TCP chat server client application together. Mainly him telling me what to type, and I'm me a little bit pretending that I understood everything, and we went from there. And at the end of these 2 days, he was pretty proud of me and was confident that I could contribute to the code base, and I wasn't at all. But yeah, anyway. So I went back the next days, and I started to actually integrate my JavaScript front end into the Haskell backend to provide the data that was needed. And actually what I did is I just brute forced the compiler messages, right? So anytime I got some message here, right? Here you can see, for example, well, type error. We expected an int, but actually we wanted a list of characters or a string at that point. Oh no, it's the other way around, right? And I just try to figure out, well, what do I have to put there to make this work? And this is a simple example here. I think it's quite forward what you have to do, and sometimes it's not. But then I had awesome colleagues. I could ask for help. What should I have to put in this hole? And if you're not so lucky to work in a company like that, then you can also ask the Haskell community, which is really, really helpful in all these situations. And they try to explain it in depth so that that you understand and that you can continue writing Haskell. So the message kind of like is you shouldn't be really scared to learn Haskell. I agree, when you look at it the first time, you don't understand it. At least I didn't. And but you still should just stick with it and try to write code with the least features or anything, right? So don't fall into this. A lot of people, when they learn Haskell, they fall into this kind of hole of trying to understand all the abstract concepts behind it. But from my personal opinion, that's not even necessary, right? So what happens is you start and you define let's just take an example here. So I define a data type called option A. It's an optional type, right? It takes a type argument that you might know from Java generics or TypeScript generics, and it could either have this value or it's nothing, it's empty, right? So you define this type. And then while writing your application code, you discover, well, you want to write a function that changes what's inside this optional value, right? So you write this first function that I put on the slide next, update optional, or update opt, right? So what it does is it takes a function that takes a value A, transforms it to a value B, then an option of A, and gives you back an option of B. And then basically you have to fill the blanks. So the first line I say, well, I have the function and I have a value inside with the pattern matching I mentioned earlier. So what I do is I apply the function to the argument inside and return some of that result, right? And in the case if it's none, the value that I try to apply the function to, will I return none again because there's nothing to do in this case. And you write a lot of code like this, and what happens over time, you or your coworkers or the Haskell community will tell you, well, look, this idea, what you're writing down here, is actually can actually be transferred to an abstract concept called functor, right? And they show you this abstract version, and you see in the type signature, it's the idea is very similar to what you had with your option type earlier, right? So you have some functor f. You have a function from A to B, and then you have an F holding an A, and you get back an F holding a B, right? So the idea is similar, and as you already used these concepts without knowing them, you kind of already have an intuition of what this should do, right? And then this makes it really easy if you start then to read up what the actual abstract concept should mean, okay? So you start kind of like the other way around. You start to do it in a conventional way, and then you learn what concept is behind it, right? Okay, so now that I kind of got to know Haskell and I got productive, let me talk about the application I meant. So it's called Checkpad MED, and it's basically a really, really large Haskell project with 1,200 modules of Haskell code. And what we do is we bring hospital medical data of patients and lab results and radiology reports to mobile devices like iPads in this example, or iPhones, or even in the web browser for doctors in the hospital. And we do a lot of data integration work, and basically this is a simplified version of a pipeline. And I see the emojis are not working here, but anyway. So on the top left hand side, you see the documents that come from the hospital, right? They have various formats like HL7, that's a very clinic-specific format. DICOM, that's an image exchange format that is used in hospitals, and also XML files, and these things are imported by one of our services, right? And in this import step, we basically trying to get rid of all these custom or different various data formats and normalize it into one single format, in this case XML. So the next step is we interpret this data, right? So because you have a generic notion of a patient or of a lab report, but every hospital wants it to be displayed in a different way, right? So some want that if your lab value is abnormal, they want to be red, others want it to be blue, and stuff like that. So we do kind of like the logic interpretation of the data. And then we write the result again into a format called safe copy. That's Haskell specific or known from a Haskell library. I will explain. And final step is a synchronizing server that actually then takes this pre-processed data and pushes it out to all our clients, right? So that can be anything from a web front end to, for example, an iOS device. And then you see the happy user, which is just this question mark with his device reading the data. And we use protocol buffers for communication at that point. Right. So let's just try and follow the pipeline a little bit. So what we start out with is this HL7 message, which I just printed here. It's a really ugly format, and it's text-based, right? And what you see is it's basically you have rows that have an identifier in the first place, and then you have pipe symbols that you know from maybe CSV or something like that to separate the fields, and then you have the data of the fields. And then there's also these tilde and these hats and whatnot to put more structure today. And in Germany, a lot of medical data is sent around like that. And so what we have to do is we have to parse this data using Haskell to understand it, right? So what do we do to bring this data to Haskell? Well, we define data types in Haskell that represent the structure of these messages, right? So for example, we have to define a top level data type called message that contains segments, right? So it's a vector of segments. That's what I said earlier. Each line you see all the way in the top is called a segment. And then the segment has a name. That's the first component of the line, like MSH or PIDs for patient identification. And then these segments, they have fields, right? So the next data type is segments with a name and the contained fields. And then we have the fields. Now the fields are a little bit more complicated. I simplified it a little bit here for this talk. So a field can either be an empty field, right? So if there's just two pipe signs next to each other, there's no value inside, so we just treat it as an empty field. But you still need to know that this empty field exists because, as you can tell from the format above, or as you know from CSV, that the position of an element is actually important, right? Because you want to later then, when you interpret this data, know that in segment number, patient identification, field number 5 is the name of the patient, for example, right? So then we have a text field that's just plain text content, and you can also then continue to structure these fields and have multiple fields inside fields, something like that. So we represent this in the last case here down here with the structured field option, right? So now we have a Haskell description of the HL7 message, and the next step is to parse it, right? So we define a function parse HL7 that takes a byte string, and it returns either an error because we couldn't parse it, or it returns the structured message, the parsed HL7 message. Now I omitted the implementation here, but it's just important to say that Haskell is a really great language to write parsers in. You have a high-level combinator library that you can kind of like compose different parsing methods, and then you still get out a pretty efficient parser. So if you are interested in that, check that out and Google parsing in Haskell. Now another thing that comes up when you do software development is that you kind of want to write tests that your code is correct, because even though in Haskell you have a strong type system, you can still mess up your business logic, right? You can still, I don't know, put in plus instead of a minus sign, or instead of, in a parser case, you expect a pipe sign instead of, I don't know, a plus sign or whatever. And we also learned this the hard way in Checkpad. So when we started out to write the application, we didn't have any unit tests at all. We thought, well, a Haskell type system will do a job of protecting us, and we fell pretty bad. And so now we agreed that Haskell needs unit tests. Right, so, but the cool thing is that writing unit tests in Haskell is actually really easy, because if you look at the parse HL7 function, you discover that the type signature already tells you what you need to put into the function and what you will get out of the function, right? So we put in any byte string, we get out either an error or the parsed message, right? And there's no hidden dependencies. This parse HL7 function can't read from a database, it can't access global state, etc., right? So when you write your unit test, all you need to do is, well, you write parse HL7 from some string that I just put in there, and you have a test framework that provides some combinators. You write should be, and well, in this case, I provided a valid message, so I should get out a valid message with a segment patient identification and so on, right? And if I just put some garbage string inside, I should get some error, right? So this is really nice to write unit tests, because you don't need to have some setup code and some teardown code to make sure that the database is running, and because you don't see it in the function, but it still accesses the database, etc. So what you get out of this is kind of like this. I would just, for visualization, I put an arrow here. So as I said earlier, from byte string right to this either error message. And now, as a lot of recent discussion is coming up about microservices, is that you can use this function, and you're really free where you want to plug this function, right? You can just use this function, as I did in the test code, inside your project, in your code, freely like that. Or you can, hook it up to a TCP stream, for example, right? So you just get raw bytes from your TCP stream, you put them in the function, and then you get a message out, and in this case we would serialize it again and send it as a byte string. Or you write an HTTP JSON interface that gives you, gets in some wrapped byte representation in JSON and returns some structured message, in this case, in JSON format, right? And you could also mix these components. So it's really a nice way of also thinking that these pure functions are not only easy to test, you can also, as you know the dependencies, really easy extract them and use them and chunk them into independent services, right? So the next thing we're going to look at is our HL7 server, right? So now we can understand, we can parse HL7 functions to a structured way. Now we want to do something with them. So we have, again, documents from the hospital coming into our server, and the server will parse them. It will convert them into some normalized format, and write them into XML, for example, and write them to disk so we can process them later. And it also will reply to the person that sent us the HL7 message that we received it and that we understood it, right? Because it's at least it's medical data, health data, so doctors make decisions on this data, so we have to kind of get some kind of assurance that the data is actually arrived and processed correctly. And the cool thing is, again, in Haskell, we can just write down this pipeline using a library called conduits. I a little bit simplified it here, but this is just to get the idea. And you just write down the way that your data pipeline looks like, and then you can plug in the functions that I said earlier, right? So in this example here, we have a source delivering us byte strings, and so we have a function called server application. It takes an argument that's a source delivering byte strings, that has a sink that receives byte strings again, and then we can put in a message function that takes a message and generates a new message, right? And it can also do I/O in this case for writing the received message to disk, for example. And now we just write, okay, we have the source, we connect our source to our HL7 parser, then we map over all the parsed messages and, for example, write them to disk, generate a response, we serialize this response again, we, I don't know, print this message through some log file, and finally we send it back out, right? So it's pretty easy to understand what happens here, and it's very, very nice for modeling these kind of data pipelines. Right. So the next step here was this import service that takes these different formats, right? And now we have them in XML. And the problem we ran into is that, well, hospital data constantly changes, right? So, for example, well, now we generate XML files of a patient, but the patient, for example, they put in his wrong first name. So the XML file will get updated by a new HL7 message that changes the name, right? Or for lab reports, you get a lab report, there's a lab value, and then before they have some preliminary analysis, and when the final analysis gets out, maybe they add some recommendations for a doctor. So we don't only have static documents lying around, so these documents also change. So to make sure that we can generate new objects that are synchronized to our end devices, we need to kind of like listen to these changes and then reflect them in the next step of our pipeline. Right. So, for example, here we have two lab values on the left-hand side, and they will be used to generate a single lab view. Right. So, just you can imagine a HTML page that just displays all the values in a tabular way. Then we also have a task number 1 that you can see at the top. That goes into there. So maybe a doctor created a task that was attached to this lab report saying, well, please check this again because this is not true, or this can't be true, something like that, right? And then the next thing that you would imagine, if you think in terms of UI, you would have an overview of all lab reports. So what's the dependency of this overview? Well, it needs the 2 previously generated lab reports or lab report views, right? And then if you think of it in another step up, you have the patient record, right? So the patient overview page that will link to the lab overview, right? And this doesn't only depend on this, but also on the patient space data, like the name, because you want to display it all the way at the top. And so to keep track of all these dependencies, we wrote a small framework, a Haskell framework, where you can sort of define a function, and it looks like you're just reading this value once and doing some transformation and returning something. But what happens behind the scenes is that that we also track what you read and capture this as a dependency. And every time one of these values changes, we rerun your computation and we give you, and then you can do the transformation again, right? So in this example, we have a laboratory report, as I said earlier. It takes 2 arguments, a patient ID and a lab ID, and returns a new lab XML. What we do is we load the patient information HL7 message, we load some lab HL7 message for this patient, and then we generate this view, right? And we use the patient's name to display somewhere in there. And as I said earlier, if one of these dependencies or both changes, then this computation will be rerun. So Haskell's not only great for just visualizing and modeling data pipelines, you can also abstract away a lot of complex ideas that you would otherwise have to write down by hand. You can hide them in a nice way that end users don't have to, or library consumers or developers don't have to worry about these ideas anymore. All right, and a last concept I would like to introduce is that once you wrote this binary format, or once you arrive at the final representation, you have to store it before you synchronize it somewhere. And Haskell has a nice library that was introduced that is called SafeCopy that handles migrations for you, which means that if you write binary objects and you change them later in your code, you can write a logic migration in your code, and the new version will automatically read old versions, right? So if you read an old version, it will read it in the old binary format, then convert it on logic level to the new data type you were working on, and you won't notice anything, right? So it handles these migrations for you. That's pretty pretty cool thing. But the bad thing about this is that I have to say is that it only works in one way. So only the new server can read old versions, but the old server can't read new versions. That's why it's that's why we can't use it in the final step of our pipeline. Okay, so that's just a few examples of how you can use Haskell to more efficiently write or structure your code. So let's look at building and tooling. Right, so let's start with libraries. So back when we started 5 years ago, actually the ecosystem wasn't that great yet. So there were only a few libraries that were usable. And now we had to write a lot of them from scratch. But this has really significantly changed in the last 5 years. So I think now you can really say that the library ecosystem is pretty mature. You can find basically libraries for anything, for data processing, for web frameworks. You have XML parsers, you have JSON libraries. So there's a lot of, it's pretty what you would expect from a major language. But what we have to say at this point is that we still lack some very high-level libraries, right? So there's not too many libraries for the sort of problem that, well, I want a user management system that you have from Node.js. I think it's called Passport or something like that. So libraries like on this level, there are not too many of that yet, sadly. Right, and so when you have these libraries, you also need a build tool that can build your dependencies. And a problem that occurred in Haskell very frequently in large code bases, so we have about 200 direct package dependencies, is that the packages, they want different versions, right? So in this case, on the left-hand side, we have a package A that needs packages B and C both need D. So this is all great till the point that B and C need different versions of D, right? And then you have version constraints and it's gonna come up with a big mess. So what was developed in Haskell was that they take snapshots of the entire Haskell ecosystem that are consistent with each other, which is a huge, huge time saver for us because before we manually did this, kind of brute forced which versions work together, and now there's a service and a tooling system that does that for us. So this is solved. But we can't only use the Haskell build tool, we also have to compile, I don't know, some external libraries to run our Haskell code or generate some code. So we need a build system on top of that, right? So basically, you could say, well, just use make. It'll work. And we did actually use make, but the problem is that the build process is very complex, and it was a really hard time to figure out in the make files what happens because you need to write parsers that extract Haskell dependencies, etc., etc. And so this nice Haskell library appeared where you also get a DSL for describing your build system in Haskell. And now we use Shake. So that's the Haskell library. So it looks a little bit similar like a make file, but it's actually a Haskell DSL that gets type checked. And you also describe your dependencies, and it will track for you, and it will allow you to do incremental builds for your project. Right. So another thing you will hit when developing Haskell, at least at large scale, the compiler is pretty slow. So I think it's comparable to the Rust compiler that we already heard about today. The thing is, when you develop small libraries, it's not really a big issue. But when you have a large project, you need to start to cache intermediate compilation results to make sure that your compilation is sufficiently fast. The IDE situation is pretty immature. So there are many editor plugins, and you can work with them, and they work on libraries and on the usual applications. But if you have a large application like ours, these tools start to run into its boundaries. And the refactoring helpers that you are used from, for example, from coming from Java, are not all there yet, like renaming an identifier. So there's still some ongoing work, but I think this, maybe if you wait another year or something, this will be solved because there's a lot of effort put into this at the moment. Right. Another thing that we hit again is, well, as I said earlier, Haskell is lazy, and so when you write a function like this that just counts up in an accumulator, well, the counting up isn't directly evaluated at the moment that you write accumulator +1. The compiler only remembers that we should accumulate this accumulator later on, and so you get this huge stack of of notions that, oh yes, I have to accumulate the accumulator at one point, but it's not actually executed until it's actually needed this value, right? These issues can be hard to track down, and above you see a memory graph from one of our production systems. When you have that, then you have to really be a Haskell or be very proficient with Haskell to know where you're going. But you only hit these when you write large code, so when you're only writing small applications, it shouldn't be a big problem. Right, so I'm running out of time, so I'm going to skip over the last front-end part and just say one thing. Just say one more thing. So Haskell doesn't only work in the back end, it also works in the front end, and this is pretty cool because you can now share the API between both and use the type system to make sure that they work together, right? And then you just compile your backend with the usual Haskell compiler, and you also compile on the API package, and you also compile your front-end package against this API package, and then you get an API for free. Right, so that's the end of the talk. Thanks for listening, and I think I can take one more question. Thank you.